Okay, so we're going to talk about the distributions for sampling proportions. Um, so if the value of p, which is our true probability, is unknown, or our unknown proportion is unknown to an investigator, what we do is we need to find that. So generally they take some sample of a certain size, and then you look at the number of successes in the sample over the sample size. So, for instance, if you were trying to estimate the percentage of heads um, on coin tosses, you would want to flip coins in order to figure that out. So let's say we flipped coins, 100 times. So we would say n to be 100, and the number of heads. Let's say we got 51. So this represents our success rate because we're looking for heads. Um, if we were looking for tails, that would be our success. But in this case, we're looking at heads. So p hat, which is our estimated proportion or our sample proportion, would in this case be 51, the number of successes, divided by the total number of trials. So you could leave it in this form 51 out of 100, or you could say that that's also 51%. So this would be what p hat would be. So when we're referencing a sample proportion, we're talking about percentages. Some general properties for sampling distributions. Again, sampling distributions, we talk about this variable p hat. It's like p with a little kind of arrow kind of thing over it. First rule is that when we look at the whole distribution of every possible proportion, the mean of our sampling proportion will be the same as the true proportion over time. So that is true. And then we have here that our standard deviation for our sampling proportion works like this, where you do the proportion multiplied by its complement. You then divide by n, and then take the square root of the entire thing. This is going to work very well, but you never want to use more than 10% of the total population, or else sometimes you could get this information could be a little skewed. Now, if n is large, and p is not too near 0 or 1, you're going to have a sampling proportion that's approximately normal. And I'll explain that in a minute. There's a very easy rule to figure this out, but basically the larger n is, the more likely you are to have a normal distribution, and the closer p is to 1/2, so like 50%, like right in the middle, the better chance you have of something being normal. But both of these kind of work together. The general rule that we use to determine whether or not you can use the normal distribution to kind of calculate things for our sampling distributions is this. You need two things to occur. You're going to want n times p, so the number of trials times your probability, to be greater than or equal to 10, and you want n times the other the complement of your probabilities to also be greater than or equal to 10. So how can we judge that real quick? Well, let's say that a batter who's up to bat has a probability of hitting at 300. So we're saying like this is going to be 300. So in baseball, that means 3 out of 10, or 30%. Now, 1 minus p would be the chance that it doesn't get a hit. So that would equal 0.700. Okay, you don't need the extra zeros. I'm just continuing with my example. Well, you need a sample size that is going to create a number over 10 when multiplied by 0.3 and 0.7. So the best way to think about this is pick the number that's smaller, whatever's going to be smaller, and you need a sample size at least enough to give yourself 10 occurrences. So for this to happen, okay, we would need n times p, which is 0.3, to be greater than or equal to 10. Now you should be able to find that n would have to be greater than 30 in order for this to happen. Greater than or equal to 30 for that to happen. Now, if on the other side, 0.7 times n has to be greater than or equal to 10, this would be a little bit different number. You would have 100 divided by, or 10, excuse me, 10 divided by 0.7, which would be 100 over 7, which you need n to be greater than, 14, greater than or equal to 14-ish. So these two have to work together. This includes every number from 14 up. This includes every number from 30 up. They have to combine together. So for this distribution, talking about a baseball player who hits 300, in order for us to use the normal distribution to approximate things for that particular player, we would need at least 30 at-bats in order to say that. You would not use this other number over here. It's too small. You always want to use a larger sample size. But this general rule is going to hold for everything that we do. So we need to know that this is true before we use the normal distribution to solve problems.